Okay, so we're going to start talking about milestone 4. And thank you to all the brave souls who came here right before a midterm. Actually, one thing I want to do before that, very quickly, let me get rid of this slide deck and switch over here. Okay, so I updated the milestone 3 unit tests, so the exercise tests last night. Because some people said that they correctly flagged that some of them were too hard. So I found a bug in our A-star algorithm and corrected it. So it actually makes the animations work better too. So the animations actually kind of led me to the bug because as I was watching the algorithm, I was like, that seems the A-star heuristic that we had unintentionally broken. So it was not a lower bound, which meant we were being really aggressive in searching, too aggressive. So again, this is Dijkstra. So Dijkstra expands out in all directions. So I'm going now from here over to here, and let's see what it looks like. You kind of see it goes all over the place. Let me turn that on to A star, and this is now a corrected A star. See, we've got a lot of different algorithms in here. So let's run this corrected A star. That one might have been hard to see, but let's say I go down over here. It basically explores, especially if I'm near a highway, you'll see that it figures out pretty quickly. It doesn't have to explore everything. So sometimes it still explores a lot, but if it can find a fast path pretty quickly, it doesn't do much backward exploration. So I showed you that yesterday, but it was with an algorithm that had a bug in it. So those pictures are more, typical of what you would get with A star. Okay, so I'm now on to milestone 4. So I know you're all going, milestone 3 is old hat. Let's talk about the last milestone. So milestone 4, the problem definition is you're optimizing the delivery route for a courier company. So this is a variation on the traveling salesman problem that you might have heard of, but we changed the problem a little bit, which you'll find is pretty common in your career. You can learn from algorithms that you've heard about, but usually exactly what you have to solve is a bit different. So you still have to apply some of your own ideas. So the problem definition is I've got a delivery truck, and I work for a company that has multiple delivery truck depots. So at night, previous drivers have dropped off their trucks, and they've dropped them off not in one place, but we got 3 different parking lots. So I can pick up a truck from any one of those parking lots to start my day. And then I've got a bunch of deliveries to make. So what I'm showing here is the green up arrows are pickups. So I got to pick up a package from there. And that package is package A. I've got to drop it off here. Okay. That's not everything I have to do. I also have to pick up package. That's not pick up. I have to pick up package B from up here. And I got to drop it off down here. And so on. So for this particular delivery person, we've got 4 packages to pick up and to drop off. So you've got N deliveries. In this case, N is 4. And every one of those deliveries gives 2 intersections. What intersection am I going to pick it up at, and what intersection am I going to drop it off at? You also are given M courier depots. So in this case, actually this we're getting rid of this here to simplify things a bit. So you've got M courier depots. In this case, it's 3. So I've got 3 different places where I can pick a truck back, and I've got 4 different deliveries to make. And to simplify things a bit, your truck has infinite capacity. So you have no constraint on how many things you might have on the truck at any one time. Okay, so what do you have to do? Given that input, you need to return a path, so a travel path, and we want it to have low time. So we'd like it to be good. It needs to start at a depot where you pick up your truck. It needs to end at a depot. Could be the same one, or it could be a different one. But you got to drop your truck off at the end of the day. And you have to make all N deliveries by traversing these intersections. And there's an ordering dependency. I cannot drop off package A until I've picked it up. Okay, so I need to go through this intersection to pick up the package before I can say that I've dropped it off by going through that intersection. Okay, so possible solutions. So possible solution, this might look like a solution. So what have I drawn here? I start off at this depot. I go to this location, which is a drop off. Then I go to this location where I pick up package D. Then I go off to um, drop off package A, and so on. Okay, so this path does go through, starts at a depot, ends at a depot. That's good. It does go through all of the intersections that we care about, where we have pickups or drop offs, but it's not legal. It's not legal because I'm dropping off packages like package B here before I've picked it up. I pick it up much later in my route, right? I have to go all the way around here before I pick it up. Um, I could go back. So if I came back through this intersection later, then it's fine. Then it would be legal. Like you don't have to avoid intersections, but you won't be counted as delivering something unless it's on your truck and you go through the drop off place. Okay. What's your output? So this is a legal solution. So now I've changed this to actually be legal. If you walk through this whole solution, I start at this depot, I pick up a package, I drop off a package, pick up a package, pick up another package, go all the way over here, drop one off, pick up the last package, make my last couple of drop offs, and then go to a depot. So that one's legal. Okay, it satisfies all my ordering constraints and it goes through all the intersections that I need to. Your output is going to be defined in the M4 header file. Basically, it's a vector, and each element in the vector basically encodes going from some interesting intersection to another one. So this, for example, would be the first entry in the vector for this solution. So vector entry 0 in my vector of courier subpaths would go from this depot to this drop off. And let me change my color so you can see this better. Okay, so maybe green is better for this. Whoops. So I go from there. Oops, I didn't actually change the color after all. Okay, I'll try this again. So I can start from here to here. That's the first part of my route, going from this depot to this drop off. That will be the first entry in my solution. So if I have a vector of that represents my solution, this is going to be vector entry 0. Okay, what's in that vector entry 0? Well, it's a data structure called a subpath that we define in the header file. What's in that subpath? It's basically the intersection ID of the start, the intersection ID of the end, and another vector is inside this, which is basically the the vector of street segments that you traversed in between. So that sounds a lot like what you had for M3, where you were given a start intersection and an end intersection, and you returned a vector of street segments. That's on purpose. Clearly, the subpath is effectively the solution to one path problem from milestone 3. So you can use your milestone 3 code, and you will use your milestone 3 code in milestone 4. Okay, but that would be just the first entry that I showed you. The second entry would be going, from this intersection to this intersection, and it would follow these street segments. So this is going to be, my solution of 1, right? And it's going to have those 3 data members in that subpath: the start, intersection, the end, and the vector of street segments. Okay. Actually, I saw a question, how aggressive are the performance targets? So the performance targets aren't aggressive. You're basically given a fixed time to solve this. So you're given 50 seconds. Okay, 50 seconds is plenty of time to solve this. We give you some small problems where 50 seconds is really long. You'll probably get bored and you might just stop your program. And we give you some bigger problems where 50 seconds is certainly adequate to get a solution, but it doesn't let you explore the space maybe as much as you'd like. You have to be efficient. Okay, so it's different. Yeah, so you do as much optimization as you can within a fixed time budget. Okay, so it's always good to think of what is a simple solution. Can you get anything working quickly? Because that's kind of the principle of agile development. So let's see, how can you reuse your M3 Pathfinder? So there's lots of ways you could do this, but what's the simplest thing you can think of? Wow, maybe this is too people are already talking about things that are way more complicated in the chat, so maybe I have to give you the simple solution. So my simplest solution I can think of is I'm just going to reuse the pathfinding algorithm I have for milestone 3, and I'm just going to connect things in the order they're given to me. So I'm going to go from the first depot that is given to me by the as input to my function to the first package pickup. So I'm just going to call my find path between intersections routine, and I'm basically, maybe there are several depots, so there are several options. I'm just arbitrarily picking the first one, and I'm going to go to the first delivery, the pickup location. So I'm going to get my first package. Okay. Um, Now I need to complete the deliveries. So I'm just going to complete them in the order they were given to me. So there are n elements, n deliveries that I need to make. I'm just going to go through from the first one to the last one. I'm going to make those deliveries. So what I need to do is, I've already picked up something. I'm going to go and go from that intersection where I picked it up to wherever I'm supposed to drop it off. Okay, so that completes my first delivery. And now I'm going to go pick up I'm at the drop off location. Okay, so I've dropped off a package. So I picked up something and I went and dropped it off. Let me change my color here. So I picked up something. Now I've dropped it off. And now I want to go get the next package. So I'll go to the next pickup location. So there's a pickup there. And that's what I'm doing here. So I was at the drop off. Now I'm just going to go to the next pickup location, call my find path again. Um, when I break out of this loop, I haven't made my last delivery. I need to go to the last drop off. So I'll do that. And then I got to drop off my truck. I'm just going to drop it off at the first depot again. Okay, so there might be a bunch of different depots. I'm just going to go from the intersection I'm at right now, my last drop off, to the first depot that you gave me as an option. So I haven't exercised any cleverness at all. Just whatever order you gave me the deliveries to do, I'm doing them in that order. Okay, so it is uh, a naive solution, as people have noted in the chat. Okay, so let's see what that looks like for this sample case I gave you. Okay, so we start at the first depot that we were given. We don't apply any intelligence whatsoever. And we go to the first package pickup, which is going to be A. So I go all the way over there, and then I'm going to go drop it off. And it needs to be dropped off over here. So we'll go drop that off. Then I need to pick up the second package, which is B. It's up here. So I go to get that. Then I need to drop it off, go down here, and so on. So I go through all this. And at the very end, I go back to the same depot. It doesn't look great, right? So you see, I'm going back and forth on 401 over and over again. There's a lot of driving. This is with 4 deliveries to make, but we're going to give you problems with 100 deliveries to make. So this is a lot of extraneous driving. It'll be even worse if you had 100 things to make. But it is legal, so we could get a solution going pretty quickly, and maybe that's a good thing for us to do. Okay, so there are a lot more logical solutions. So if I look at this as a human and just go, well, there's something I could pick up that's really close to this depot. So I'll start at this depot and I'll go pick up that package, and then it's actually pretty close to the drop off, so I'm just going to drop it off. And then from there, I could, what could I do? So I've started at this depot, and I've gone and picked something up and then dropped it off. What should I do next? What would you do if you're just sitting in your car, you don't have a computer, but you are deciding on this delivery route right now? So go to the closest pickup. Yeah. So that's actually probably a likely thing you'd do yourself if you had no computer, no pen and paper, and you're just optimizing this in your head. You'd probably go to the next pickup that's close, and that's the closest pickup. So I'm going to go there. Then I'm just going to immediately drop it off. Well, in this case, actually, my algorithm's a little smarter still. I'm basically going to go to the next something else that's close by, and then I'm going to go drop that off. Then I'm going to go pick that up, drop that off, and so on. So this one's a lot better. I used a little more intelligence. I tried to check, is there something else nearby that I could do, and go there. And if I go back and look at the previous path, there's a lot more driving here than there is in this solution. And this solution wasn't very hard. I basically, at any point, just decided what's nearby and went to it. Okay, and I see Isidore saying in the chat, that's a good thought. So I'm going to come back to you in a minute. Okay, so we need to optimize the delivery order. So the point of this is that it matters a lot. It already matters when I only have 4 deliveries to make. If I have 100, the difference between a really good delivery order and a really bad delivery order will be, factors, probably 30 times less travel, 40 times less travel. So it's the difference between having a 6 hour workday and a 1 month long workday. Okay, so maybe we could just do this perfectly. So in milestone 3, you're actually writing algorithms that are basically perfect, and you're just trying to make them fast. So we should check. Maybe there's a perfect algorithm that we could use and get the best possible answer. So an exhaustive algorithm. We could just maybe try all possible delivery orders and then pick the one with the lowest travel time. Okay. So how many combinations? And I can see people are thinking this is actually a lot. Okay. So let's see. I've got M truck depots. All right. And it is a lot. Okay. So I've got M truck depots and I've got N deliveries to make. So each delivery is actually both a pickup and a drop off. So it's actually 2N intersections. So I have to make a decision of one of M starting locations, pick my depot. Then I have to make a decision of one of these 2N pickup or drop off intersections. Then I have to pick, okay, the one that I've already done, I'm not going to go back to, but I have to pick one of 2N minus 1 choices for the second intersection, pick up or drop off that I make, and so on. I have to keep doing this till the last delivery. And then finally, I have to drop my truck off at the closest depot. So there are M of these again, M choices of where to go. So how much is that? I have to pick one of M depots to start at, and then it's factorial. I needed to pick one of 2N intersections to go to next, pick up or drop off, and so on. As I complete deliveries, there are fewer choices, but still quite a few. So this is factorial. Um, I didn't put the final M in because technically, if I'm at a depot, I could just drop it off at the very end. I don't really need to evaluate all possible choices of depot for all combinations of what happened before. I can just go to the closest one. So I don't wind up with a last factor of M. But this is a big number. Okay, it's M times 2 to the n factorial. Um, Now you could say, well, maybe it's a bit high. This 2 to the n factorial, some of these are illegal. Like you could go back here and you could say, well, you said you can go to one of 2N intersections, but actually N of those are illegal because I don't have anything on the truck yet. So only the pickups make sense. So that's true. Let's say I just write the algorithm though, where I generate all of these possible orders and then I check whether they're legal or not as part of my evaluation. So I check if it's legal and then I check if it's good. Um, that's actually a lot easier to code than trying to make sure I don't generate illegal ones. And it's not going to be that much faster. It would cut this a bit if I was more clever and never generated some of the illegal ones, but it's still going to be a really big number. Okay, how? So we basically worked out we could write, relatively straightforward exhaustive algorithm, but the number of combinations that has to check is really big. M times 2N factorial for M depots. That's not going to be too big a number, and N deliveries, which will be reasonably big. So some of the cases we're going to give you are, at least this big. The biggest ones actually can be a bit bigger than this still, but 10 depots and 100 deliveries to make. So let's plug in some numbers. So that means we have 10 times 2 to the n factorial possible orders, which is 10 to the 377th, approximately. So it's a big number. How fast a computer do I need to handle that? It's going to have to be really, really fast. Okay. Now, let's say my algorithm, the way I'm also going to evaluate every one of these solutions is I'm going to evaluate every one of these delivery orders with the algorithm I had before. I'm going to invoke my find path function to connect all of these intersections, figure out how long it takes to go between them. So for every one of these orders, I'm going to invoke my find path function 2 to the n plus 1 times, because I'm going to invoke it to go from the depot to the first delivery, then I'm going to invoke it again to the next intersection, and so on. So if I have 100 pickups, 100 drop offs, and a depot on each end, the number of paths that I need to invoke my find path for is 2 to the n plus 1. Okay, so let's say I wrote a really good find path, and it takes about a tenth of a second per call, which is quite good. If I multiply all this out, I get a time of over 10 to the 378ths. And I see someone saying get that many cores and do it in parallel. Yes, this is huge. If I convert this to years instead of seconds, it's 10 to the 370 years. The universe is estimated to be about 14 billion years old. So yeah, this is never going to work. No matter how fast a computer you try to throw at it, it's unbelievably slow. It's unimaginably slow. So obviously, an exhaustive algorithm is completely out of the question. We're going to have to do something more clever. And for this problem, that more clever solution is not going to be guaranteed to get optimal answers. Okay, so we're solving a variation of the traveling salesman problem. It's embedded in a graph, so we actually have to do some extra computations, some path searches to figure out how far apart intersections are in travel time. And we've got an extra constraint of we have this ordering dependency between certain intersections. Like we need to make pickups before we do drop-offs. But it is a variation of the traveling salesman problem. So the traveling salesman problem is a well-known computationally hard problem. And so, yeah, do you know what a computationally hard problem is? So you studied this in 244. Okay. So some people know what it is, but you didn't discover it. So I haven't studied it. So yeah, it basically means NP hard, right? Computationally hard and NP hard are basically the same thing. Computationally hard is just kind of catches NP complete and NP hard. There are a few different, slightly different subcategories. Computationally hard is basically encompasses a larger category of you don't have any polynomial time solution. Okay, so what do I mean by that? So we have n deliveries to make. There is no guaranteed optimal algorithm. So an algorithm that is guaranteed to produce the best or lowest travel time solution in polynomial time. Okay, what does that mean? So it means that the order of any algorithm that could guarantee it got the optimal answer must be worse than n to the k. Okay, n's the number of deliveries for any k. We can't make k any constant. So it is worse than n squared. It's worse than n cubed. It is worse than n to the 10,000 for sufficiently big n. What does that mean? In practice, that means that it's at least exponential. Okay, we can't bound it by any polynomial in n. And exponential algorithms take a very long time as n gets big. They basically are impractical for n not very small. Okay, so what do you do then? So lots of interesting problems. In fact, most of the problems that people do research on from an algorithm point of view are computationally hard, because otherwise you can just solve them and say I've got an optimal solution. So you don't give up, but you use heuristics to solve them. So does anybody, what is a heuristic? What does heuristic mean? So we have to use heuristics to solve this. What does that actually mean? Yeah, basically, a heuristic is like an educated guess. So it's and when applied to an algorithm, it means seems like a good idea, right? Can't prove that this is optimal. It's a heuristic. I'm just gonna try it because it seems smart to me. I'm gonna measure it. And we'll see how well it works. And that's basically what you usually have to use for computationally hard problems. And it's actually where a lot of cleverness comes in. This means everybody can think of, well, what seems like a good idea to you, and no one has come up with like the best idea. There's always room for improvement. Okay, so most research problems are computationally hard, and they come up with all sorts of stuff. So there are lots of them in one of my research areas, which is integrated circuit design, but also in drug design, where they're trying to figure out how proteins will fold, how to optimize a city. So when you get into problems of not finding travel paths through an existing city, but you start thinking about how would you design a city, those become NP hard, and so on. So there are a lot of them. And one of the pioneers of complexity theory, which more formally defines what is computationally hard, is actually at U of T. So Stephen Cook, a professor in computer science. Uh, has anybody heard of Stephen Cook? How many people know of Stephen Cook's name? Okay, so it rings a bell for Isidore. Maybe not others. Okay, don't worry about it. I'm going to tell you a little bit about him really quickly. Okay, so there are NP complete problems, which means that there are no NP complete problems are problems where there's no polynomial time solution known on conventional computers. So basically, a more formal definition of the computationally hard uh, description I just gave you. What Stephen Cook did, so there was this notation of NP complete that existed before he did his research, but what he did is he proved that if a method is found to solve any of these problems, and there are a lot of them, okay, protein folding, things in integrated circuit design, etc. If a method is ever found, breaking encryption, etc., if a method is found to solve any of them in polynomial time, all of these problems can actually be transformed into each other so that all of these problems can be solved in polynomial time, which is actually a pretty interesting result, right? So all these complicated problems have something in common, even though they seem very different. If we can ever find an algorithm to solve one of them optimally, we can solve them all optimally in a reasonable time. So this is actually the most famous open problem in theoretical computer science, at least, of P versus NP. So P is the class of algorithms and problems where we can solve optimally in polynomial time. So n to the n squared or n cubed or n to the k. And NP is all of these problems where we need to use solution techniques that are at least exponential if we want to guarantee optimality. And no one has been able to show that there isn't an algorithm that could solve these NP problems in polynomial time. And if somebody finds an algorithm for one of them, then every single problem in this whole NP, all these complicated ones, will basically move to P. They'll all be solvable in polynomial time. So if you want a high risk research project, you could basically go research this, trying to prove that P and NP are equal. No one's been able to prove it. But basically, he created this problem. He's the one who showed that this existed. If you could solve one of these NP complete problems optimally in reasonable time, you can solve them all. So that became known as the P versus NP problem. Can you find that algorithm? This is an interesting exercise in kind of like resilience. So Stephen Cook was actually denied tenure in 1970 at UC Berkeley, and that would be it's a very hard experience for an academic. So the way tenure works is you get your PhDs, you work hard, you become a professor, you work very hard for 6 to 7 years, trying to come up with research results, publishing papers, etc. And at the end of that time, a committee evaluates is it good enough or not? And if it's good enough, you're given tenure and you basically have a job for life. And if they decide that's not enough, you're denied tenure and you actually have to leave. So so it's very weird for 6 or 7 years. You just kind of work away, hoping you're doing well, and at the end of that, you're either given a job for life or you're fired, which is unusual. Most companies don't work this way. Yeah, it is kind of illogical, actually. So I agree with the comment in the chat. So yeah, this is kind of you've been working so hard for so many years. It's like not a really happy occasion. But he moved to University of Toronto, so he didn't give up. And in 1971, 1 year later, he published his most famous paper. So the paper that set this P versus NP and showed this result. In 1982, he won the computer science equivalent of the Nobel Prize, the Turing Award. So it's the highest prize in computer science, named after the famous computer science pioneer Alan Turing. And apparently after that, Berkeley actually called him up and said, if you want to come back to Berkeley, we'll give you tenure now, which must have been kind of a nice turnaround. He said no. I'm guessing I don't know exactly how he said no, but it it's a good exercise in resilience, right? So um, not everything works out the way that you initially expected, but it can work out in the end anyway. Okay, so that was about optimality, and you're basically not going to get an optimal algorithm for this. So what we're going to do instead, are we're going to use heuristic algorithms, and I'm going to talk about one pretty reasonable heuristic algorithm is pretty easy to code. So on milestone 4, you can kind of decide how far you want to go on milestone 4. You can get a pretty reasonable answer pretty quickly, or you can work on for essentially as long as you want, trying more and more complex algorithms. Okay, so actually the ideas, Isidore actually already came up with a pretty good idea of this, which was basically we could start at any depot and go to the nearest pickup. And while we still got packages to deliver, we're going to drop off the package at drop that package off at wherever it's supposed to go, and we're going to go pick up the nearest remaining thing. Okay, we'll keep doing that, and then we'll go to the nearest depot at the end to drop the truck off. So, what's the computational complexity of that? Well, we're at a certain depot. We've got a bunch of depots, and we have to pick which one we're going to start at. So we're going to evaluate what's from a depot to some delivery, what would be the shortest path? Okay, so to evaluate that, we actually have to look at all the depots, m of them, and we have to look at all the pickup locations, n of them, and figure out which of those possible starting paths is the shortest. So that's an order m times n computation. That's how many combinations there are. Okay. What about this? What's the complexity of this loop? Yeah, so Daniel, you're right. You could probably do this nearest check in a smarter way. So right now I'm doing it in a brute force way. I'm just gonna like check. I want to see what's the shortest path from a depot to an intersection to some pickup, and I'm just gonna check them all. So, but you're right. You might be able to optimize that. What about this loop? How many times am I going to go through this loop? Yeah, so order m times n. Order m n times number of packages. Well, let's see. We're going to go through this loop n times. I think I actually have this animated, so let's do this. Because I've got n deliveries to make. And for every one of them, this dropping off the package is fine. That's just constant work. The find the nearest remaining pickup, I'm going to again do that in a straightforward way. I'm just going to like compute what the travel time is to every one of those pickups. Okay, so that's order n because I'm at some intersection, right, where I've dropped something off, and I'm going to go figure out my travel time to every pickup location that there is. So that's an order n computation. And then at the end, I go to the nearest depot. So I'm at some location. I just check all the depots. That's order m. I just have to check all the depots that are there. Okay, so if I combine all that together, I get this order m times n plus n squared. So an awful lot better than factorial. It's n squared, so it's not really low, but it's practical. I can do something in n squared as long as n doesn't get too big. Okay, so let's see if this is fast enough. Okay, so I told you that we're going to give you problems about 100 deliveries and 10 depots. So if I plug in those numbers, um, it's going to be about 11,000 times however long it takes me to evaluate these travel times when I'm making decisions on what to do next. Let's say I'm going to call find path to evaluate every one of the travel times. So I want to know how long to go from where I am now to some potential next pickup. I can call my M3 find path. That'll tell me exactly what the answer is. But that's about zero point 0.1 seconds for a pretty fast find path. And that means that this is about 1100 seconds. So it's nowhere near lifetime of the universe, so way better, but it's still too big. Okay? Because we're going to give you 50 seconds. So this is still too long. What do you think? How can I make this faster? So this algorithm's not bad, and it's not looking at too many options, but it's still taking too long. Let's see. So how can I make this faster? So Wei Hang is saying Pre-compute the time between every legal pair of A to B. Yeah, so that's a good idea. We might be able to pre-compute this and just look it up over and over again. Okay, so pre-compute the paths. And we're going to talk about that next week. That's a good idea. Any other ideas? Let's say I don't know how to do this. I don't want to do this. Basically, if I pre-compute all the paths between these things, so that's about 100 squared over two different paths, which is still too many, right? So if I pre-compute them all, that's about 5,000 calls to find path, which is also going to be too much. Okay, so pre-compute's a good idea, but we're going to have to find a smarter way to pre-compute than to just call our find path over and over again. Um, the other thing we can do, let's say I want to just get a solution going quickly. Okay, um, what you can do is you can estimate the travel time as being proportional to the geometric distance. It's not perfect, but it's much faster. It's an order one computation that's very quick. Now your time to your C is maybe 10 to the negative seventh, maybe even less. And now you'll be able to run this algorithm in about a millisecond. After this algorithm is done, you still have to run find path a couple of hundred times to actually connect your delivery order together. So basically now getting your delivery order is going to be very fast. If I just use this estimate of what my travel time is while optimizing delivery order, I can get delivery order really quickly, and then I'll just fill in the find paths at the end. Yeah, and you could do various. I see people saying, "Well, sort by Euclidean distance, and then only consider those," and those are all reasonable. So I'm saying I'm going to use Euclidean distance completely, pick my delivery order, and then just hook things together. You could do blended approaches where you use geometric distance to prune down how many options, and then use find path for those ones. Okay. Um, so yeah, I'm going to get my delivery order really fast now. My final connect all these things together. I still have to connect all the deliveries together. I'll call find path on my all these intersections to hook them up, and that's about 200 calls, but that's 20 seconds, which is well under my 50s, so I'm okay. So it's a practical algorithm, and it actually works reasonably well. So on this example, it would actually go and do this. Okay, so let's see. Let me go back a bit. It would look at the various depots and the various pickups, and it would say, okay, this one is going to give me the shortest initial connection. And from there, it's going to look at, well, I'm just going to go drop it off. So it's not going to think, it's just going to go drop it off here. Then it's going to say, well, what's my next closest pickup? It's that. And it's not going to think, it's just going to drop it off here, and so on. Okay. And at the very end, we wind up at our last drop off, and we just go to whatever depot is closest. So it's a lot better than using the given or random order. But maybe you can improve it more. So, how can you improve it more? Yeah, so Isidore's already got how do we improve it more. One of the things that this algorithm is doing is it's kind of constraining itself a bit more than it has to. So it basically has to go make a pickup first, but after that, it could either do another pickup or do a drop off. And it's only considering that I'm going to immediately drop this thing off. Okay, so it's not considering the whole space. Yeah, so what we can do instead is actually exactly what Isidore said. We're going to keep the same style of algorithm, but we're going to evaluate when we decide what to do next. We're going to consider all the choices of what we can do next. So we're going to still go from any depot to the nearest pickup. And then while we have packages deliver, we're going to go to the nearest legal pickup or drop off. So we'll consider both. And then we add that into our solution. And we keep doing that until we run out of packages to deliver. So this isn't actually much extra code. And at the end, we drop off the truck at the nearest depot. Okay, if we analyze the complexity of this, it's still order m times n at the start. We'll now go through this loop 2n times, and finding what's the nearest legal pickup or drop off is still order n, and then final order m at the end. So the actual overall computational complexity hasn't changed. It's order m times n plus n squared. That was the same as before. The constant in front has changed a bit, so it's a little more work, but it's not too much. Okay, and it works better. So if we take that, do you remember what the prior solution looked like? If we just use this algorithm, we'll again look for the closest depot to some pickup. So it's that one again. But now we'll evaluate not just going to this drop off, but also are there any pickups that are closer? And there is. So we'll pick this up. And now we could drop off A, which is here. We could drop off D. We could pick up B. We could pick up C. So it considers all the things I could do next. And it decides I'll drop off D. And again, it looks at everything at every stage that it could do next. And eventually it's done everything. It drops off at the last depot. And if you compare this to what we had, this is lower travel time. Okay, so both these heuristics, I can see people are commenting on us in the chat. They're both given a name of they're greedy. So I'm calling this heuristic one and heuristic one plus plus. Heuristic one plus plus is not much more code and it works better, so that's probably where you'd want to start. They make the next decision greedily. They always make the best decision that they can make without ever revisiting any earlier decisions. So they live a life without regret. They decide to do something. They never change any earlier decisions. Greedy algorithms are generally fast, but they often don't get the best solution. You can make them smarter if instead of just deciding what to do next by saying what is the very next um, destination that I can go to that has the lowest travel time, you could have it consider, well, what happens after that? If I do that, what would happen the next step after that? And by having a little bit of look ahead, trying to think a couple steps ahead, these algorithms still can make a decision and always live with it, but they can do better by looking a little further into the future of if I make this next decision of going, I'm at this intersection and I might go here or I might go there. I don't want to decide that based just on the travel time to those two places. I also want to consider what would be my next best option right after that. And maybe this intersection would be a legal one where I could pick up or drop off, and therefore that's a better place to go. So I basically decide then I'll go here, right? That's the next place I'll go, even though if I just look one step ahead, I can't tell. Now that I'm there, I don't not committed to go to this intersection. I basically do the same thing again. From here, I'll look at what are all the places I can go and maybe what happens after that. And now I might decide, well, I'm going to go here. Okay, because when I look two steps ahead, that's the next best place to go. So yeah, so greedy algorithms, pretty easy to code, pretty fast. Um, Generally don't get the best solution. There are special cases where they can, but this is not one of those special cases. You can make them a bit smarter by adding things like looking a couple steps ahead. Sometimes you can come up with other insights of ideas. For example, we might want to um, take into account that if we do a pickup instead of a drop off, we gain more flexibility. Right now, our algorithm doesn't have any notion of that. It just considers it equally good to do. Here, I've done a pickup, and it considers it equally good to go do a drop off or to do another pickup. But if I do another pickup, I actually gain more flexibility for future decisions. Maybe I should consider that when I'm deciding what to do next. So, so greedy algorithms are a very broad class of problems. You can make them smarter by having guesses of what's going to happen in the future after they make the next decision. And that means even though they never go back and revisit a decision, they have a bit better prediction and they can get better answers. Okay, and that was as far as I was going to go today. And I think you guys probably need to go off to your midterm. So I'll hang around in case anybody wants to ask a question, but I suspect all of you are heading to the midterm. Good luck on it.